So let's go ahead and move into a little bit more in-depth of thermography and these different, the different parts of the process here. So thermography is what's known as an indirect process. Most of what we've been studying up to this point are considered direct processes. And that is for an indirect process, so I'll actually go ahead. Direct process, radiography, ultrasound, eddy current, we are injecting some kind of an energy into a test object. Right? So for ultrasound, we're sending a pulse into an object. For eddy current, we're sending a magnetic field that induces currents, which create their own magnetic field, then we can detect with our eddy current tester. Right? And X-ray radiography, X-ray or gamma ray radiography, we send radiation through a part. Right? We see how it passes through. We'll talk about that in the next unit. And we measure it after it's gone through the part. But it's not actually being absorbed by the part. Okay, it's not actually heating the part or cooling the part. I mean, sometimes when we perform like mag particle, right, the part heats up, but that's kind of a side effect of just running current through it. And so for thermography, we're going to do it, it's what's called an indirect. And so what happens is our part has to absorb energy, whether we put put it in an area like an oven or in front of a heat lamp to absorb, or out in the sun to absorb that energy. And then the part's going to lose energy. Take it out of the oven, you take it away from the heat lamp, you move it out into the shade. But that energy was kind of stored, it was kinetic energy that was built up in the part. Okay, and whether you're imaging it as it warms up or imaging it as it cools down, you can do it either way. But it's the energy transfer is taking place due to diffusion. It's not our test itself that is inducing that energy in there. It's something we're doing as excitation, but the actual measurement of it is kind of a separate process. And so parts or anything that has heat added to it, when you move it into an environment without heat, or if you move it from an area without heat into an area with heat or infrared, it's going to emit or absorb infrared radiation. It's always going to be giving off a certain amount, so we can measure that. So we're not actually injecting a pulse into it. We're not actually injecting a magnetic field into it. We're not injecting X-ray into it. We're not magnetizing or running current through it. So that's where the term indirect comes from. And so what I mean by that here is where we can see kind of that breakdown of what happens when infrared energy hits a part. So on the left, coming in from the top left, you've got another name for it, incident shortwave radiation. Infrared energy. Okay. And it's going to hit our part, and a certain amount of it is going to be absorbed. A certain amount of it's going to be reflected. Okay. It ends up coming off as a longer wave. It increases the wave size when it's reflected. There's a little bit of it. Some of it may even be transmitted, a very small amount, depending on the thickness of the part or how big it is. Right? Some might be emitted from the opposite side. But what's then going to happen is that energy that's absorbed is going to then make its way back out of the part into the environment. And that's the emitted radiation. That's what we're imaging. That's what we're looking at when we shoot a picture of this with a thermal camera. And so, but what will happen is the thermal camera will also pick up reflected radiation. So one of the things we have to do is calibrate our equipment, let it know how much of that energy it'll see. Our camera is going to see the radiated energy. It's also going to see the reflected energy. And it's just going to see it as energy. So we have to tell it how much of that energy is being reflected off the part. And the way we do that is by telling the camera essentially what percentage of heat is radiated versus what percentage is emitted. And that's known as the emissivity. So we don't want this. We don't want this. We want to look at this. This is to kind of remind you what a direct process is. So it's not this ultrasonic, this is. So when we do this, the geometry of the part is going to affect how the surface temperature responds. And we'll reach something called a limit of detectability. And this is the ratio. Any damage to a surface or any discontinuity surface is going to have a certain diameter. And if it's like an oval, we're talking the minor diameter here, versus the depth. And typically the diameter divided by the depth needs to be greater than 1 to get an accurate reading. So what that means is it's good for wide area detection, but what you're not going to see are very narrow cracks. Okay, it's not great at finding the narrow cracks like you would find with eddy current testing. It's not great at finding the narrow cracks you would find with dye penetrant or with mag particle. But what it is good at finding is things that tend to be wider area, impact damage in a composite surface, crushing of the honeycomb in a metal surface, if you have like a metal honeycomb, or water that's made its way into inside of an object that kind of spreads out, that diffuses out. That's what you're going to find. So, and then the other thing you have to look at is what are called contrasting thermal properties. How much is that damage? How much is that water? How much is that crushed area? How different is that from the surrounding material? The more similar they are, the harder it is to detect those differences. Water, its thermal properties are significantly different, water and ice, than fiberglass. It's going to show up. It's either going to be, if it's when you're warming up, the water's going to stay cold longer. When you're cooling down, the water's going to stay warm longer. It's going to be obvious. But if you have, an impact damage where there isn't much separation, maybe you have a little bit of air in there, but it's going to be harder to see. So that's that contrasting thermal property. So the more contrast there is, in their thermal properties, the bigger the difference in thermal properties, the easier it's going to be to see something. And that also applies to their diffusivity, how quickly the heat transfers through a part, as well is going to make a difference. A repaired area that's solid, made of like a solid material, is going to conduct heat much different than the honeycomb right next to it. And so that heat's going to diffuse through it differently as well. When we take our image, one of the things we got to understand with and keep in mind when we're performing thermography is that the apparent size, what it looks like in the camera, what it looks like when we take the image, can differ, and sometimes significantly, it can differ from the actual size of the damage or what it is we're imaging. Because that heat, there's a hysteresis. It takes time for that diffusion to take place. There's kind of a sweet spot. When you say you put something in an oven to heat it up and you take it out to image it. When you first start imaging it, that heat's going to be everywhere. Everything's going to be about the same temperature. And so you're not going to see much right away. Maybe 5 minutes later, you might see a big contrast between the thin metal areas and the thick metal areas, right? The thicker areas are going to hold the heat more. They're going to retain more energy. Thin areas are going to cool off faster. And then as it sits longer, maybe 10 minutes or 15 minutes after that, now it starts to become all the same temperature at that cooler, back to room temperature again. Well, you'll get the best true size when there's a sweet spot there. Things will look fuzzy when it's all too warm, right? It's all too similar. Things will look fuzzy when it's all too cold, because again, they're all too similar. But by imaging it over time, you can find that sweet spot where you can actually make measurements where your measurements become more accurate. So the more contrast you have, the more contrast you have, the the more accurate the apparent size is to the true size of a flaw. And so that kind of takes some practice. That takes imaging over time, analyzing a few different images and kind of looking for which one has the best contrast, which one makes, is showing. But when we're direct viewing, the big thing you got to do is that if you have a hot area surrounded by colder areas, that heat's always going to be transferring out a little bit. It's going to make whatever that hot area look bigger, right? Because it's kind of working its way out into the surrounding structure. So it's going to be blurry, so to speak, or you're going to have that slight difference. It's going to make it look bigger than what it is. The apparent size often is bigger than what the true size is. And then that comes into play. That's really important when you're doing a quantitative analysis and there's a maximum damage limit, for instance. You want to make sure that you're careful about, is it exceeding that limit? So to increase that accuracy, oftentimes what's done is pixel processing, where a computer, an algorithm looks at those temperatures pixel by pixel. And based on the behavior, it's comparing pixels next to each other and surrounding each other. There are algorithms out there that can really nail down, like, where is the damage and where is it just the heat diffusing into the surrounding area. As the lateral dimension approaches the detection limit, i.e. as you get deeper without larger distance, that can also reduce the accuracy. And then early process acquisition, that is less affected by diffusion of energy. But again, the contrast may not be 69. That's what I said. When you first pull the part out, the whole thing is going to be the same temperature. There's not going to be much contrast. As the areas that lose heat faster start to lose heat, you're going to get more contrast. But again, if you go too long, that heat all starts to diffuse into those areas, and you lose that. You lose some contrast. So again, it's hitting that sweet spot. This is just another reminder of what direct view versus pixel processing looks like. The direct view at the top, that's the flap of an airplane, and that's what moisture ingress looks like. So this airplane had flown, it landed, it flew, it was up at altitude for hours, right? Got cold soaked at negative 20 to 40 degrees, came down and landed. The fiberglass flap is warming up to ground temperature while the water inside is taking longer to heat back up. And so it shows up as moisture inside of it. This is a common inspection on a lot of Airbus aircraft. Boeing is doing it more and more too. Airbus was kind of the first to get it. Below is pixel processing, where it's looking at each pixel individually, and a computer would kind of start to pick out patterns and that kind of thing. A little more in-depth look at different excitation techniques. So remember, qualitative is your often used for in-service. That's what this is right here, this top one. This is a qualitative inspection. Now it might get to a point where it's, okay, let's measure how much water is in there, right? But initially it's just, is there water in the flap or not? Pixel processing. Okay, now count the pixels that make up the areas of water versus the areas that don't. What percentage of the flap has moisture ingress? So that's getting into the quantity. Qualitative, easy and quick, minimal equipment, pretty much just your camera. Most of what you're going to be doing for the lab, pretty much everything you're doing is going to be qualitative based. Although you can do some measurements by then going in and doing area measurements. The temperature changes are using camera after landing, moving indoors if you're sitting in the sun, opening the doors. So if you're in a temperature controlled hangar and it's cold outside, you open the doors. Aircraft are going to cool off. You're in a temperature controlled hangar, or it's been overnight, you open the doors, it's really hot outside, aircraft are going to warm up. Many other scenarios for inducing a temperature change. If you go to more of the active type thing, active excitation techniques, these are some of the common ones you'll see. So a flash type thing I've talked about. Another one is a light that's used in a scanning motion. Anyone ever been on stage? And what happens when the spotlight points at you? Well, besides going blind, you get warm for a second, right? And then it moves past you and you cool off. That's scan. That's what's going on with the scan excitation. Okay, you're taking a heat source and scanning it across the surface. And then typically what happens is the camera's following behind it. Taking picture, picture, picture. So it heats up and cools down here. So you can actually scan across like a large surface area. You can do, we'll look at what step and modulating, we'll look at those are different ways of doing lighting. So all these on A on the left are different lighting techniques. B is demonstrating, we've got the hair dryer there. That's demonstrating convection, using hot air. And below is cold air, an air conditioner. You can even put an air conditioner blowing on something, although it's really hard to control it precisely, but you can. You get one of the portable air conditioners and blow cold air somewhere and just see how that heat leaves an object. C over there is demonstrating direct contact. That's a heat blanket. I really wish we had a hot bonder. Does Gail say that in structures class too? Have you ever brought up a hot bonder? Hot bonder are basically electronic heat blankets you can use when you're doing composite layouts, curing. You put them in your vacuum bag. It's basically a hot pad that gets vacuum bagged in with your part. And that heats it up instead of having to put it in an oven. You can use them for this. You lay that heat mat on there. They're very, very precise. You can heat stuff to within a fraction of a degree. So they can be very precisely controlled. Also why they're really expensive. But they're really cool to use. Projects, they were always nice. And I had to do both stuff. So active heating, quantitative, some of the things you can do, even measuring things like thickness, depth, and area. The big one here is area. Right? We're going to look at the area of damage. That's the most common way this is used. Thermal diffusivity, differences in it for things like adhesion, delamination. Okay. Oftentimes, adhesion, delamination, we can see that if we have a composite that's been damaged. You have delamination taking place. But it can also be used during the repair to see, did you properly bond your repair in place? We would have to do that. No, I didn't. This was kind of before thermal, but we'd have to do it. The Saab 340s I worked on used bonded metal skin. Have you all seen how bonded metal works? Basically using an epoxy, the epoxy ribs on. So they didn't use rivets to hold the skin to the formers and the stringers and the ribs. They were bonded. So, and it was actually 2 layers of metal that were bonded together as well. So if they got a dent in them, it could pop that apart. And particularly if that dent was in, you didn't want it to oil can and pressurize. So rather than patching an area or cutting it out and fixing it like you do with rivets, we would just basically, you would coat that area with a thick epoxy. You'd take another piece of metal and slap it on the outside. And you would vacuum bag it down and bond it. But then when we were done, we'd have to go afterwards and we had to make sure that there were no air pockets or voids in there and make sure that entire patch was bonded down tight so that it wouldn't allow the skin underneath where the dent was to oil can. You basically filled that dip with epoxy and then put a piece of metal over top of it. So you would use something like this for that, to adhesion or delamination, even in the repair process, not just in the initial investigation. You could use it to see if it was fixed properly. Here's some of those different optical techniques and what they mean. So optical is nice because we use visible light. When visible light hits certain materials, it becomes heat. Right? It puts heat into the object absorbs that energy, and then that energy is given back off as infrared radiation or heat. Big thing here, non-contact. We can use a non-contact source, right? A light is non-contact. We use a non-contact camera. We never actually have to touch the surface. It can be small to large areas. It's typically used where alignment and positioning is not super critical. You just need to heat the area up, and you need to image it while it's warming up, or you need to image it while it's cooling back down. But they can have different application patterns. So the first one is pulse. Let me go to this next page. So pulsed is shown here in orange. So light comes on, light shuts off, light comes on, light shuts off, comes on, light shuts off. It's almost like blinking. Now this can be really fast. This can be fractions of a second. You can see it's almost like a strobing effect, where the camera's taking pictures between the strobes, between the flashes, between the pulses. Step, you can see is this graphically. It goes up, 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 down, 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 and where you can take pictures as the heat sources at each of those steps. So you'll see how the how energy transfer is taking place, over time and at different energy levels. Modulated is kind of like pulsed. That's that lighter orange. You see, but there's no off time. So pulsed, you see it's on and off. You take a picture on it. Modulated is up the net, immediately starting to bring it back up again. And again, you would often have a camera that would take a picture during the low times has the least amount of reflectivity, although you can have others. And then the last one is scanned, and what they're showing is this is intensity over time at a given location. So it's not necessarily the lights turned up brighter and then dimmed. It's, imagine if I'm scanning across the surface and think about how much energy is at this crack right here, right? As I come across, it's going to start building, building, building. It's going to be at its most, and it's going to go down, down, down. And that's what's shown by the scan line right here. And that's where you would have your heat source, oftentimes with a camera following it. Okay, and then the camera is picking up what's going on behind the heat source in the areas where the heat source, the light, has already been applied. Forced air. This meme getting a little outdated. Probably time to change it. Yeah. I haven't seen the ski instructor in a while. Active heating, forced air. This is like air blowing out of the vents in the room here. Right? We heat the air, we warm the air up, everything in there gets warmed up. It's not the most efficient, but it can be used for a wide area. You pull the plane into the hangar that has a heat source, you turn on the heaters. Plane starts to warm up. Right? You put it in a paint booth, and you can really crank the heat up. But again, non-contact, small, large area, alignment, position, you just pull the plane in the hangar and turn the heat on. That's really pretty not critical, right? Heat guns, hair dryers, blowers, convection type ovens, cool air blowers, so you can decrease temperature with like an air conditioner type blower. So it doesn't necessarily have to be heating up, it can be heating up or cooling down. Some different forms of contact. Those things in the top right, those are the heating blankets from a hot bonder. So those plug into the hot bonder. The hot bonder runs a current through them, but it also monitors the temperature very, very closely. It can carefully control the amount of current. How many of you have seen one of these things on the bottom right? One person, two. How many of you had an ear infection growing up? Is it? Yeah, and your parents pull out the hot bottle and you lay on it? Yeah. Okay. You can use them for this. You can use them to heat parts up. Small to medium, right? You're not going to have a giant like heat blanket. I don't know, maybe you grab the heat blanket off your bed or something. Like your blanket. But even that's not a huge area compared to like a whole hanger. But good for thick or low diffusivity structures where it takes a lot to get that heat to make its way through an object. You need to really get it heated over time. You can put one of these hot bond mats on and leave it on there for hours. And just heat and heat, get that heat in there, and then take it off and then image it over a long time. The cameras, like the cameras we've got, one of them, they can, you can set it to take photos, individual photos. You can set it to take video, or you can do like a time. You can do like a delay time where it. You can do where it takes pictures over time. What? Time lapse. Thank you. You can take time lapse images. So if you have a thick or low diffusivity structure, it takes a long time for the heat to get in it. Think about like a brick. Anyone ever heated up a brick? We're cool. And you know, in the summer, bricks get hot. They take forever to cool back off again. You know, you go walk. How about bonfire? Anyone gone to like a bonfire pit like the next morning after you have a bonfire and it's still warm? The rocks or the bricks, right? So that's a low diffusivity structure. They're very thick. It's, you know, you have a bonfire going in the bonfire pit for a long time, and then even after the bonfire goes out, it takes a while for the bonfire pit to cool back down again. Same kind of a thing. You can run these heat sources for a long period of time, and then you can set them up in front of the camera doing time lapse, where it takes pictures over a long period of time, you know, where you don't want to stand there and snap a picture every 5 minutes for the next 3 hours. Not appropriate for rapid thermal interaction. Okay? The camera's line of sight, obviously, if you're using contact methods, you can't take a picture of the area when there's a heat blanket sitting on top of it. So simple field sources, water bottles, you can use bricks or even sandbags. You warm up, you have hot sand, put a sandbag out in the sun, let it get hot, bring it in, set it on something that heat's going to transfer into your object, pull the sandbag off, start taking your pictures. But they tend to be easier to control with, especially if you're using like a hot bonder blanket. You can vary the heat or temp, the contact time, all kinds of stuff. Some of the others, electromagnetic, induction heating, and microwave heating, must contain metals, typically ferromagnetic for induction heating. Metals in a ferromagnetic materials in a magnetic field will heat up in a change in magnetic field. You run enough current, you can get it red hot or even melt it. What you can do is put the magnet source down the center of a cylindrical object, like a pipe or tube, and then, or with microwave radiation, and then you can monitor as the heat works its way to the outside as well. Continuous scanning, that's what I was talking about, where large area, you're going to move the camera and the scanner across the surface. It's an alternative to, let's see, I'm going to inspect area A, and then I'm going to move over to area B, C. I can just continuously scan along the length of something, say a fuselage. And it can be modulated or pulsed as well by varying your. So let's leave off there, because then we're going to get into some more detail of temperature measurement next time.